Hello everyone, and welcome again to NEDL, the best platform around for distance learning in business, finance, economics, and much more. Please don't forget to subscribe to our channel and click the bell notification button below so that you never miss fresh videos and tutorials you might be interested in. My name is Sava, and today we are discussing the GARCH model, that is the Generalized autoregressive conditional hereroskedasticity volatility processes, and we will try and fit the GARCH model into the real-world data on S&P 500 return volatility. In the previous video, we have already discussed the ARCH model that has been suggested in 1982 by Robert Engel, and the GARCH model is, as it is evident from the title itself, a generalization, an extension, a further development on the ARCH model that has been proposed in 1986 by Bollerslev. And the GARCH model logically is slightly different from the ARCH model in the sense that it allows for more persistent volatility processes. If we look at the conditional volatility formula, then the first bit is remarkably similar to the one we discussed in ARCH. We have got the unconditional volatility omega that remains there no matter what. The ARCH component, that is the immediate volatility persistence given by the ARCH coefficient alpha and lagged realized volatility, lagged squared residual epsilon t minus 1 squared, and the additional component which represents the conditional volatility persistence. That is the GARCH term, the GARCH coefficient beta that, just as the ARCH coefficient fluctuates between 0 and 1, represents how persistent is the conditional volatility through time. And here, the conditional volatility at time t, Vt squared, depends on the lagged conditional volatility Vt minus 1 squared. And this one is not directly observable. That is the conditional volatility that we arrive at having already estimated the parameters of the model. So GARCH is even more of an iterative procedure than ARCH is. So it's slightly trickier to estimate its parameters. Later on, when we discuss how the realized volatility is formed, it is not different from the ARCH process. We have the conditional volatility plus the disturbance term, the error in variance, the volatility of variance, UT. And just like in ARCH, we use the maximum likelihood estimation or the log likelihood maximization to arrive at the optimal values of our parameters. But here we have 4 parameters instead of 3 that we can calibrate to arrive at the maximal value of our log likelihood. So first of all, let's start by specifying our baseline condition when we assume that there are no ARCH or GARCH processes in the volatility of stock returns. We calculate the average return, our constant, our intercept around which the returns fluctuate. Then we calculate our simple standard deviation for the sample, that is the constant volatility, and our constant variance is just standard deviation squared. And then we assume that those are the starting values of our GARCH model parameters. Our constant is just the sample average, our unconditional variance is just the sample variance, and our ARCH and GARCH coefficients are just zeros, representing that there are no ARCH or GARCH processes in the baseline case. And then we will try to calibrate those parameters to arrive at a higher value of the log likelihood function than in our baseline case. Also, we need to calculate our alpha plus beta, so the sum of the 2 parameters. And the crucial bit is that this sum should never be higher than 1, because as you remember in the ARCH model video, we have discussed how alpha gets into the formula for long-run volatility. And if alpha was higher than 1, then the infinite series would not converge and the conditional volatility in the long run would explode. In that case, long-run variance is the unconditional variance divided by 1 minus alpha minus beta. And the long-run volatility is the square root of the long-run variance, so it's the square root of unconditional variance divided by 1 minus alpha minus beta. And here, for the infinite series to converge, for our time series to have finite value of long-run volatility, we need the sum of alpha and beta to be less than 1. And that's the prominent restriction that we would enforce in our optimization algorithm. And in that case, where we have our hereroskedastic process with GARCH and GARCH coefficients equal to 0, our long-run volatility, unsurprisingly, is equal to the constant volatility. Now we can start calculating the residuals and the realized variances to then arrive at the maximum likelihood function. So the residual is just equal to the realized return, our y variable, our dependent variable, minus our intercept, our constant mu, and we'll lock that because we don't want it to change observation by observation. And then we enforce this formula for all of the observations. Then we square the residuals to arrive at realized volatilities. Then we lag the squared residuals to arrive at the lagged realized volatility. And then we need to start calculating our conditional variance from observation to observation. Just as in GARCH model calibration, we have an issue that we don't really know what the conditional variance at the start of our observation period is. And the go-to assumption to make is that the conditional variance at the first observation is equal to the long-run variance. And here we can just input unconditional variance divided by 1 minus alpha minus beta. So at the start, our conditional variance is equal to the long-run variance, and then it behaves according to the autoregressive process specified by the formula over here. So we can just input it, translating it into the language of Excel, having unconditional variance locked plus alpha, the GARCH term, times the lagged realized volatility, lagged squared residual, plus the GARCH coefficient beta times lagged conditional volatility. In our case, it would be the previous value of our conditional variance. And here we can enforce this formula and bottom right click it all the way down, and we can see, just as in the previous case, that if alpha and beta are both equal to 0, our conditional variance is constant and it's equal to the constant variance we have simply calculated beforehand. Now we need to specify our likelihood function, or our log likelihood function to be more precise, so that we can later on optimize it, maximize it, given the different values of the parameters. The log likelihood function is exactly the same as in the case of GARCH. It's just the set of variables we can change differs, so we can just input the same formula. Natural logarithm of 1 divided by the square root of 2 times pi times conditional variance, and here the square root of conditional variance, so the square root of vt squared, will give us vt in the denominator. That's exactly what we want, times the exponent of minus realized volatility, so squared residual, divided by 2 times the conditional variance. And then we close the bracket for the denominator, close the bracket for the exponent, and close the bracket for the natural log, bottom right click it all the way down, and arrive at different values for our log likelihood. And then we estimate the sum of log likelihoods. That would be the overall log likelihood function that we would like to maximize. And here, the process of the numerical optimization of the log likelihood function is slightly more complicated than in the case of GARCH, because we'll have a lot of stability conditions. We need our unconditional variance to be positive, we need our GARCH and GARCH to both be between 0 and 1, and we need our alpha plus beta to be less than 1, so that the stability condition is fulfilled. Here we need to impose a lot of various restrictions on our coefficients. So let's do exactly that. Go Data, Solver, and specify our optimization task. First of all, we need to set our objective function, and again, that's our cell with the computation of the log likelihood, so cell G8. We need to maximize that by changing the cells where our GARCH parameters are. So cells B5 to B8, the constant mu, the unconditional variance omega, and the GARCH and GARCH parameters alpha and beta respectively. And now we need to add all of the constraints we have just discussed. First of all, we need to untick the make unconstrained variables non-negative option, as we might well allow our constant to fluctuate outside of the positive domain. We might well assume that the constant can be negative. So we just need to add the constraints on omega, alpha, and beta. First of all, we need our unconditional variance to be strictly positive, so adding a constraint on cell B6. And here we can see that, again, there are no strict inequalities in the solver interface, so we can trick solver into doing what we want by imposing an unstrict inequality and requiring the unconditional variance to be greater or equal to a very small positive number, effectively requiring it to be strictly positive. Here we can set a restriction that omega is greater or equal to 1 millionth, a very small number, so 0.000001. And click OK and proceed to the restrictions on alpha and beta. For alpha and beta, we want both of those to be non-negative and less than 1, so let's proceed with that. Add a restriction on alpha and require it to be non-negative. Add a restriction on beta and require it to be non-negative as well. Add a restriction that both of those should be less than or equal to 1 for stability reasons. So B7 is less than 1 and B8 is also less than or equal to 1. And then we also need to add a restriction on their sum. So alpha and beta for stability reasons, for convergence, so that our long-run volatility is a finite value, that the process, the GARCH volatility process, is not explosive. We need to add a restriction that alpha plus beta, so cell B9, is also less than or equal to 1. And here you might be tempted to again select gradient descent and run the formula, but here we will encounter one peculiar issue with gradient descent. When you have a lot of restrictions that you need to maintain while optimizing your likelihood function, the gradient descent algorithm can fluctuate outside of the predefined boundaries and lead to calculation errors. So if you have selected gradient descent, GRG nonlinear, and click solve, you will encounter this very peculiar issue. We can see that the coefficients for alpha and beta have increased so that their sum is higher than 1. The volatility process does not converge and it leads to calculation errors in log likelihood. So how one might avoid this issue? Well, to do that, we might resort to the evolutionary search algorithm, evolutionary optimization framework, that is basically a clever brute force optimization when your computer just searches through all potential combinations of the parameters it is allowed to change to reach the optimal value and selects the one that gives you the highest result for your objective function. But there is another restriction that we need to impose. For the evolutionary algorithm to work, all the parameters, all the variables that we allow to change throughout our optimization process should have both upper and lower bounds. And it's quite intuitive why is that the case, because for brute force optimization to work, you need to have a finite set of potential values of parameters so that your computer can cope with this problem in finite time. So here we have already got both upper and lower bounds on alpha and beta, so we need to add an upper bound on unconditional variance, omega, and both upper and lower bounds on our constant mu. For omega, there is a clever way how we might select a reasonable upper bound. First of all, bear in mind that unconditional variance is itself a lower bound on conditional variance, and our average variance throughout the sample, if we assume constant volatility, is 0.000073. So we might suspect that unconditional variance should never, in any estimation, be above the simple sample variance, as in low volatility periods it is much lower than the average sample variance, and in the high volatility periods it's much higher than the average sample variance. So we should not expect unconditional variance to be higher than this value. So we need to add this restriction. B6 should be less than or equal to this value, so approximately 0.000073. And then we also need to add the restrictions, both upper and lower bounds, on our intercept, our constant mu. And here we need to resort to some arbitrary assumption about our constant? Well, first of all, the constant mu is just expected daily return, so we shouldn't really expect it to be too high or too low in terms of magnitude. So we can reasonably suspect that it cannot be, for example, higher than 0.1%. 0.1% daily return is a lot, and it cannot be really negative as well, so it cannot be lower than minus 0.1%, for example. So let's add those constraints. First of all, our constant mu cell B5 should be less than or equal to 0.1%, so less than 0.001, and it also should be higher than negative 0.1%, so greater or equal to minus 0.001. And here we have come up with all the constraints needed to successfully perform an evolutionary search algorithm. First of all, we know that some of these constraints have been imposed just arbitrarily, to be fair. So when we arrive at our optimization result, we will need to look at what those parameter values are. If they are set at the boundaries, so for example our constant would be 0.1%, or very near the boundaries, we can suspect that the choice of these arbitrary constraints has impacted the search algorithms, so we might want to revise those. If, on the other hand, the parameter values are comfortably inside the boundaries we have specified, we can be reasonably sure that the selection of those constraints did not impact the optimization process much. So now we need to select the evolutionary search algorithm and press solve and wait until the brute force algorithm converges. It takes quite a bit more time than the gradient descent algorithm because again it's just a brute force optimization procedure, but in reasonable time periods it should converge for a simple enough problem such as the GARCH parameter calibration. So in very short time we should arrive at the optimal parameter values as per the evolutionary search algorithm. And the solver has just converged on optimal parameters for our GARCH model, so we can click OK and check if our parameters make sense in terms of the boundaries we have selected. First of all, our constant is quite a bit lower than the upper boundary of 0.1% we have specified, so we can be happy about it. The unconditional variance is quite a bit higher than 1 millionth, so 0.00001. It's actually 0.00008. So again, no surprises here. We can be reasonably comfortable with the lower bounds we have imposed, and our ARCH and GARCH coefficients are slightly in the middle. Our ARCH coefficient is notably close to the ARCH coefficient we have obtained previously, so 0.34 in both cases, and our GARCH coefficient is slightly lower than 0.6. Added them together, we have 0.94, which means that the conditional volatility process is actually rather persistent. The closer it is to 1, the more persistent the variance process is. And we have obtained the value of log likelihood that's much higher than the one we have got with ARCH alone. It means that mathematically GARCH allows us to arrive at a closer approximation of the real-world volatility process. And now we can compare the results for realized volatility and GARCH and ARCH conditional volatility to see which of those approximate the real-world volatility process better, at least graphically. So to calculate realized volatility, we need to calculate the square root of realized variance, so square root of the squared residual. To calculate the realized volatility, to calculate the GARCH conditional volatility, we need to calculate the square root of GARCH conditional variance. And for ARCH conditional variance, we can just refer to the cell from the previous sheet. And now we can bottom right click it all the way down and look at the graphs we have obtained. So here we've got the realized volatility in blue, ARCH volatility in gray, and GARCH volatility in orange. And we can see that first of all, what comes to mind initially is that GARCH volatility does not have such a prominent lower bound as the ARCH model does, which is arguably more realistic. Also, the GARCH model in orange does have higher peaks than the ARCH model and comes closer to the real-world volatility spikes that are signified here in blue. So the mathematical intuition that log likelihood is higher for GARCH than for ARCH is actually verified by just looking on the graph. It means that GARCH models are extremely useful in modeling persistent volatility processes, and they capture the real world better than the ARCH model, and yet better than the constant volatility assumption. That should come as no surprise. For GARCH modeling, you need to have a very persistent volatility process. So generally a rule of thumb is when you have high frequency data, for example daily or even intraday, then GARCH is a go-to technique. If you have weekly data, bi-weekly data, or monthly data, then ARCH might be enough, as your observations are not as frequent. Furthermore, what you might have noticed in GARCH and ARCH models, in comparison to usual linear regressions like line-est output, is that we have the coefficients by all means, but we haven't got the coefficients standard errors, both in GARCH and ARCH. Actually, you can calculate the standard errors for ARCH and GARCH processes, but it's much harder than the procedure for a linear regression. Again, you cannot just multiply a bunch of matrices together, as you have no matrices. You have no independent variables in the usual sense of the term. So to calculate the standard errors for those coefficients, you have to apply some pretty sophisticated numerical procedures. We would not delve into this in that particular video, but if this videos on GARCH and ARCH models get enough likes, I will by all means do a separate video on standard error calculations for ARCH and GARCH models. As for now, that's all there is for volatility process modeling with ARCH and GARCH. Please leave a like under this video if you found it helpful. In the comments below, I'm eager to see further suggestions on videos in business, economics, or finance you would like me to record in the future. And please don't forget to subscribe to our channel. Thank you very much, and stay tuned.